Okay, let's continue. The first session we got an overview of a variety of combustion systems which are relevant to propulsion and a couple of examples which are not directly relevant to propulsion also, but the idea was to give you an overview of what fundamental aspects of combustion are required to deal with real systems. Okay. What we will do in this lecture is we will look at one such fundamental aspect which will be the idea of equilibrium. In general, we will be talking about thermodynamic equilibrium, and we will also see a couple of examples of how calculating equilibrium states is of relevance to actual systems. I will use the picture of a premixed methane air flame that you see in the screen as a sort of a working example for introducing ideas related to equilibrium. So this flame that you see in the picture is formed by a jet of close to stoichiometrically mixed methane and air. It is a premixed flame, and the mixture is issuing out of a 5 millimeter diameter metal tube from the bottom. The fuel air mixture is coming from here and ignited at the top, and a conical flame forms at the top of the burner. What I referred to as flame just now is what you see in the picture of the flame, which is the prominently visible bright blue cone. That is the flame. We will see later that this bright cone is the zone where the temperature is close to maximum, and the rate of conversion of reactants to products we will refer to as reaction rate, and the heat release rate because of conversion of the reactants to products are maximum. So this is this zone, the blue cone, bright blue cone that you see here. Away from the bright blue cone on either side, which is inside of the cone and the outside, on either side of the bright blue cone, the temperature is lower than what it is at the flame, and so are the reaction rates and the heat release rate. Okay. And therefore it is reasonable to assume that there are, let me not say no chemical reactions, but the reaction rates away from the flame are orders of magnitude smaller than the reaction rates at the flame. So there are essentially no chemical reactions happening inside and outside of the thin cone. Of course, the accurate way of saying it is in outside of the cone, what you have is a condition of equilibrium where the forward and backward reaction rates are exactly matched, but we will come to that later. So the question that we are interested in is, in scenarios like this, what is it that we can learn about the flame from the laws of thermodynamics? So that is the first fundamental idea that we will discuss in this lecture. So when considered in its entirety as a full system, all zones in the image that you see are at about the same pressure. It is a jet of methane and a premixed mixture of methane and air issuing into open atmosphere, and therefore the pressure everywhere is roughly the same, except for small differences in pressure that are required to establish the flow, which is a few pascals at maximum, and compared to the atmospheric pressure of 100,000 pascals, that variation is very small. So if you calculate the pressure as density times the gas constant times temperature, it will be the same everywhere. Therefore the system can be assumed to be in a state of physical equilibrium to a very good approximation. What we mean by that is the pressure everywhere is roughly the same, but different zones in the image are at different temperatures. Obviously the system is not in thermal equilibrium. For example, the temperature, as we saw in the previous slide, close to the flame is much higher than it is elsewhere. Okay. Also, different zones in the image have different chemical composition. Okay. Inside the cone you have predominantly reactants. At the flame the reactants are getting converted into products, and outside of the flame you have products of combustion. Okay. So the system is not in chemical equilibrium, the system is not in thermal equilibrium, but system to a very good approximation is at physical equilibrium. Okay. So when considered as a single entity, the system is not in thermal and chemical equilibrium. In fact, the chemical reactions occurring in the thin flame zone creates gradients in temperature and concentration which actively maintain a state of overall non-equilibrium. But we all know from our courses in thermodynamics that thermodynamics or the laws of thermodynamics relate properties of systems in thermodynamic equilibrium. Okay. The system has to be in a state of physical, thermal and chemical equilibrium for us to use the laws of thermodynamics to relate different properties of the system. But this does not seem to be the case when the entire flame is considered as a system, because it is not in thermal and chemical equilibrium. But what we could do is, if we divided the system into a large number of smaller boxes, okay, such that each small box or each small volume can be considered to be in thermodynamic equilibrium. This box has to be sufficiently small. We will precisely define what we mean by sufficiently small for it to be considered in thermodynamic equilibrium. Of course, the volumes cannot be divided indefinitely, because we know that if the volume is so small that it contains only a few molecules, then the macroscopic notions of temperature, density and other thermodynamic variables will become inapplicable. Okay. Therefore, what we need to do is to identify a volume which is large enough to contain sufficient number of molecules for us to meaningfully define average properties of temperature, pressure and density, but it should be at the same time be small enough to be considered at same temperature, same pressure and same chemical composition, so that the laws of thermodynamics can be used. Okay. So, this idea is what is conveyed by this pixelated image of the same flame, where each pixel can be considered to be at thermodynamic equilibrium, while the entire system is not in thermodynamic equilibrium. So, an indicator of this is the gradients in color when taken as a whole system, but each pixel when considered as a unit seems to have uniform color. The same can be taken as representation of uniform temperature and composition. So, so we will address the two aspects separately. One is how small the volume can be, and how large, so what is the lower limit and what is the upper limit. Lower limit so that thermodynamic averages can be meaningfully defined, upper limit so that the thermodynamic equilibrium assumption is valid. Okay. So, we will look at the lower limit first. So, for average properties to be meaningful, the average number of molecules in a chosen volume should be large enough for the fluctuations created by random molecular motion to be negligible. Okay. This idea is quantified using what is called relative fluctuation, which is nothing but the ratio of, if you take a small volume, relative fluctuation is nothing but the ratio of the standard deviation of the number of molecules, or fluctuation, or measure of fluctuations in the molecular concentration to the average number of molecules in that volume. Okay. So, relative fluctuation is defined as a measure of the fluctuation in the number of molecules in a chosen volume divided by the total number of, or the average number of molecules in that volume. For ideal gases, this quantity varies as 1 by square root of n. N is the number of molecules which are present in that small volume, which we know from ideal gas equation of state goes like this: square root of RT over PV times Na. Na is the Avogadro constant, which is about 6 into 10 raised to 23. So, when we calculate, or we can estimate the relative fluctuation using this relationship for a typical case, which is pressure of 1 atmosphere and a temperature of 1000 kelvins. As you can see, if you choose a volume which has let us say, imagine a cube with a side of 0.01 micron, the relative fluctuation is very large, about 51%. Large number of molecules go out and come in. So, the molecular number of molecules in the volume fluctuate a lot when you have a volume that is as small as 0.01 micron, and as the size of the cube increases, when we get to about a micron, the fluctuation has come down by a large factor. It is now only 0.051%. Okay. And when you get to a 1 mm cube, the relative fluctuation is, for every million molecule, only about 2 molecules leave, okay, on an average the volume. So, starting from about 0.1 micron, we can consider the volume to have sufficiently large number of molecules with minimal fluctuation for averages to be meaningfully defined. Okay. So, with this we now have a limit on what the smallest volume can be. Therefore, macroscopic properties like temperature and pressure can be defined and measured as long as the volume of focus is a sphere or a cube, whichever is convenient for you to imagine. You can take that. I think cubes are easier because that is how we divide domains when we do computational simulations. Okay. So a cube of side not more than size more than 0.1 microns. When we have more than 0.1 microns, at 0.1 microns the relative fluctuation is about only 1.6%, and then it drops very quickly as the volume increases. So as long as the size is more than about 0.1 micron, we do not have to worry about the validity of the average properties. This in essence is the continuum assumption, and for such differential volumes, thermodynamic laws in the form of differential equations can be used to relate various properties and their spatial and temporal relationships, which we call as the Navier-Stokes equation, which we use for simulating flows and reactions through different combustion systems. Now we can move on to the next limit, which is how large can the volume be to be considered in thermodynamic equilibrium. But to answer this question, we need to have some estimate of a length scale of relevance to flames, which we will call the thickness of the flame. This is because of the fact that sharpest change in thermodynamic variables occur across the flame. The thin bright blue cone we see in the picture, which we saw in the picture in the previous slide, the thickness of that entity is the thickness over which the variables change significantly, and therefore we need to make sure that the volumes that we choose are smaller so that the changes are not large. Okay, so a good measure of that size is the thickness of the flame. So what is the thickness of the flame? That is the next question. To answer this question, we need an estimate of the flame thickness. This is because of the fact that, well, I am repeating this point, the sharpest changes in thermodynamic variables occur across the flame. Okay, the thin bright blue cone we saw in the pictures above. Okay, this is something important. This is something that we will use many times in this course. The thickness of the premix flame that we are looking at is controlled by two processes. One is the speed with which heat is generated due to chemical reactions, okay, which raises the temperature in that domain, okay, and the other process is the diffusion of heat away from the high temperature flame to the low temperature surroundings. What I mean by that is, remember that when you set up the experiment in a lab, you have a steady blue flame, okay, and if you measure the temperature of the flame, it does not change with time, but the products, the reactants are continuously getting converted into products and heat is being generated, and unless the heat is removed from the reaction zone at about this, at the same rate, the temperature cannot remain steady. Okay, that the temperature remains steady means that heat is removed at the same rate that it is being generated, okay, and this process, this balance is what is maintaining the temperature profile. Okay, so this reaction diffusion balance will have a length scale, which, like for any reaction diffusion process, will go as square root of a diffusivity multiplied by a time scale. Okay, the alpha is the thermal diffusivity measured in meter square per second, and Tr, T subscript R, is the reaction time. Okay, this is also another feature that you will see in analysis of mass transport, heat transport, and momentum transport. Whenever a process is controlled by a diffusion reaction balance, the length scale associated with that process will be proportional to square root of diffusivity times a time scale. Here the relevant diffusivity is the diffusion coefficient of heat, and the relevant times, the diffusivity that is relevant is the thermal diffusivity. The relevant time scale is the reaction time scale. A time scale associated with reaction is simply you have a small volume where reactants are getting converted into products. So the time for reaction is simply the amount of reactants present in that volume divided by the rate at which the reactants are getting consumed. Okay, so the time scale for the reaction is the mass inside a chosen volume divided by the speed of the chemical reaction. So you have a certain amount of reactant present in a volume, certain kilograms of or certain grams of reactant present in a volume. The speed of the chemical reaction is the rate at which that reactant is getting consumed, which is grams of the reactant consumed per second. Okay, and we are looking at a small volume, so both the numerator and denominator are divided by the volume, so it becomes the density inside that volume divided by the speed of the chemical reaction inside that volume. Okay. So, that the density divided by the speed of the chemical reaction, which is denoted as omega dot. Omega dot is related to the flame speed or the burning velocity, which was discussed in the first lecture. Do not worry about the precise functional form of this, we will look at this, we will derive this in a later lecture. What I want you to notice is that the reaction rate is proportional to the flame speed squared. So, that is something that is intuitive to us. Faster the flame propagates, higher is the reactivity. Okay. Faster the flame propagates, faster is the reaction, and therefore smaller is the time scale for reaction. That alone I would like you to recognize now. The precise relationship we will look at later. So, now we have an expression for the reaction rate and the reaction time. Okay. Now, we can estimate the thickness, which when you plug in the expression for omega dot into delta going as square root of alpha TR, you will find that delta goes as alpha over the flame speed. This is also something that is intuitive. Faster the burning or faster is the reaction, faster the flame propagates, thinner is the reaction zone. Okay. So, two things I want to reiterate: the reaction rate is higher when the flame speed is higher, okay, and the reaction zone thickness is smaller for higher flame speeds. Okay. Yes. We are looking at the example that we are looking at is a premix flame. So, premix flame, an important controlling parameter which determines the flame speed of a premix flame is the rate of the reaction. So, we are looking at a scenario where the reaction rates are happening in a finite period of time. That infinitely fast chemistry is an assumption that is more relevant for cases where the fuel and the oxidizer are not premixed. So, there the what becomes more relevant is the time it takes for the fuel and oxidizer to mix, and that time is much smaller than the time it takes for the reactions to happen, and therefore infinitely fast chemistry is relevant there. In a situation where the reactants are already premixed, there is the mixing time, there is no such thing as mixing time, they are already mixed. What controls the processes is the speed of the chemical reaction. So, it is a finite rate chemistry situation where it cannot be assumed. If you assume that the reaction rate is infinite, you will also come to the conclusion that the flame speed is infinite, which is not correct. Any other questions? Yeah.
So, this flame, the location of the flame, and we have been discussing about flame thickness, which essentially involves the diffusion of the heat and the diffusion of species into the flame zone.
Correct.
Where the turbulence interaction also comes into picture. Yeah. And the assumption of this delta n over n, where we are taking about the number of molecules entering into the control volume and exceeding, is that if the turbulent length scales are in comparison to that, then our assumption is not taking that into account.
Yeah. Anyway, we will have a detailed discussion on this. The only point that I want to make here is the turbulent length scale, the smallest turbulent length scale is limited by not really. I mean the smallest turbulent scale is limited by the length scale and time scale at which processes become dominated by laminar diffusion based dissipation. Right. That is a Kolmogorov scale, and that scale is still much larger than the volumes where relative fluctuations can become larger. Okay. Any other question? Yeah.
Here the elements which you have considered, we have said that the flame has two zones. One is the actual flame zone where the temperature is very high and the reactivity is high, and the peripheral zone where the reactivity goes down and relatively the temperature goes down. So we are considering homogeneously similar elements across the entire region. So where the fluctuation is higher or where the drop is drastic, are we not supposed to take more finer elements so
that
capture that?
That is correct, and that is the reason why we are estimating the thickness of the flame, so that the volume that we choose is not much larger than that, so that
we are homogenizing it.
Yes, the assumption of homogeneity is maintained. I just
one point he made, the outer zone temperature will be higher.
I made a mistake there. Yes, the statement that I made is not correct. Where did I make it? Yeah, this statement is not correct. I said that away from the bright blue cone on either side the temperature drops, it is not correct. Only on the inside the temperature drops, outside the temperature will be equilibrium temperature. I should thank you for pointing that out. Yeah.
So, and one more thing.
Yeah.
For considering the volume that we are going to, suppose we are going to model a combustion zone, we will be emphasizing more on the chemical equilibrium also, where the species will not have a difference of gradients.
Correct.
So, when that comes into picture, how are you taking that assumption into this and considering the volume of the control system?
Yeah, so the reason why we are trying to get an estimate for the size of the largest volume that we can pick is so that the state of the temperature of the gases inside and the chemical composition inside can be considered or can be taken to be homogeneous. It means there is no variation in space.
Because of higher, when you have a higher fluctuation constant,
correct.
Definitely we have a higher diffusion of masses into the control volume.
That is correct.
Obviously,
that is why we are choosing.
Chemical homogeneity.
That is why we are choosing a volume that is such that the relative fluctuations are smaller, and at the same time not too large so that the gradients are significant. Once we get an estimate for the flame thickness, you will see the point that I am making. Yeah. So now. With the expression for the reaction rate, we can get an estimate for the thickness of the flame. I have given a few examples of flame speed and flame thickness. The most common example is methane air stoichiometric mixture, which has a flame speed of about 40 centimeters per second. For that case, the flame thickness is about 250 microns. Okay. So now I would like you to compare this with the volumes at which relative fluctuations become significant. It is 0.1 microns. So if I pick the volume around the flame, which is only 10 microns, let us say a cube of size 10 microns, I can reasonably assume that the gradients are significant over a length scale of 250 microns. So I can take a volume that is 10 microns, 10 micron cube, the gradients will be smaller and the 10 micron is sufficiently large for us to meaningfully define thermodynamic properties. Correct. Yeah. So it is 250 microns for methane air. Even for methane oxygen, it is about 25 microns. Hydrogen air is 33 microns, hydrogen oxygen is 5 microns. Therefore, under all these conditions, the flame is sufficiently thick for relative fluctuations to be negligible, and continuum assumption is still valid. So the thickness over which the temperature change is significant. The temperature change is significant, is much larger than what is required for the continuum assumption to be valid. Therefore, in a volume about the thickness of the flame, we can ask questions of the following sort: what is the temperature of the flame? What is the chemical composition of the products of combustion? Okay. And these are the questions that are answered by thermodynamic equilibrium considerations. Okay. It is clear that the length scales are such that the laws of thermodynamics can be meaningfully applied. I have not explicitly shown that the time scales also follow the same kind of behavior. I leave it as an exercise for you to to do something outside of this lecture. Yeah. So just a quick overview of the laws of thermodynamics. Now that we have convinced ourselves that we can apply the laws of thermodynamics, let us quickly go over the equations. The first law is the law of conservation of energy. When applied to a fixed mass undergoing a process, it is simply the difference between the heat transferred and the work done is equal to the change in the internal energy of the mass, okay, which can be expressed when we only allow for displacement work or pressure volume work. The work interaction is PdV. Therefore, the equation can be expressed either as in the form of internal energy or as enthalpy. Enthalpy is simply internal energy plus PV. Okay. And the second law is the law of entropy, which says that when you have an isolated system which can be split into a system plus a surrounding, the entropy change for the system plus the entropy change for the surrounding will always be greater than or equal to 0. Okay. So now the entropy change for the surrounding is the heat that is transferred from the system to the surroundings, which is negative delta Q, which is the heat that is lost from the system divided by the temperature of the surroundings. This is the definition of entropy, okay, which this delta Q can now be expressed as using first law as du plus PdV or dH minus VdP, that is not plus. Okay. So when you substitute this back into the expression for delta Q, you will end up with an expression of this kind, which is du plus PdV minus temperature of the surrounding, and D system is greater than or equal to 0. I am emphasizing this fact that the temperature that we are talking about is the temperature of the surroundings, okay, because when the system undergoes an irreversible process, we do not actually have a way of defining the temperature for the system. Is greater than or equal to 0. This is the minimum Helmholtz free energy statement. Instead of an expression in terms of internal energy, if you use the expression in terms of enthalpy, you will end up with this expression, which is dH minus VdP minus T surrounding the entropy change of the system is greater than or equal to 0. Okay. So, what these statements mean is that when you consider a system at constant volume, look at this expression. When you consider a system at constant volume, you have du minus T surrounding ds system is greater than or equal to 0. So, when the system is away from equilibrium, this quantity is greater than 0, and when the system approaches equilibrium, it reaches 0. Okay. So, similarly here also you have dH minus VdP. When you consider a system at constant pressure, you have dH minus T surrounding d system ds system is greater than or equal to 0, which is a statement of minimum Gibbs free energy. When the system is away from equilibrium, the Gibbs free energy is higher, and when it is at equilibrium, it is lower. Yeah.
So, D system, ds of system, why are we not using the system temperature but the surrounding temperature?
You may not always be able to define a system temperature. For example, if you have identified a certain mass as your system, if it undergoes a quasi-static process where it shifts from one equilibrium state to another equilibrium state where the process is happening slowly, at every point along the process you can identify a temperature, pressure and so on, but that may not be the case always. When it is undergoing a fast process, which may happen in fact in a real system, as in the case of the flame that I showed, okay, it may so happen that the system goes through a fast change where you cannot actually know the state of the system at every intermediate state. So, you do not know the temperature, you know the temperature at the beginning, you know the temperature at the end, but not in between. Okay. Yeah. At a given temperature and a fixed total pressure, the equilibrium composition can be determined by minimization of the Gibbs free energy. Under conditions of constant volume, we can determine it by minimizing the Helmholtz free energy. This is essentially what the NASA chemical equilibrium and analysis software does, which I am sure practitioners of propulsion design use on a daily basis. So, this tool can be used to calculate the equilibrium state, and the corresponding temperature is called the adiabatic flame temperature, and the concentrations will be the composition in the post flame gases. So, in the post flame gases, the temperature will be equal to the adiabatic flame temperature. Of course, I am assuming that heat losses are negligible, I am assuming that the system is adiabatic, and the concentrations will be corresponding to the equilibrium concentration. Okay. We will have a demonstration of NASA CEA at the end of the lecture, but before moving on to a demonstration of calculation of equilibrium states using NASA CEA, let us take a quick overview of stoichiometry and energy changes of chemical reactions. I have taken this simple case to this, many of you may be familiar with. The stoichiometric oxidizer to fuel ratio is nothing but the ratio of the mass of the oxidizer to the mass of the fuel. The mass of the oxidizer should be such that it has enough oxygen to convert all carbon into carbon dioxide and all hydrogen into H2O. I have shown a simple example of methane stoichiometric equation. The oxidizer to fuel ratio for this is 17.2. In the table on the right hand side, the same thing is shown for a variety of fuels with both oxygen as the oxidizer and air as the oxidizer. For hydrogen, the oxygen to fuel ratio is 8 and the air to fuel ratio is 34 and so on. Some interesting fuels that I want you to notice are some metals. You see that magnesium is listed as a fuel, aluminum is listed as a fuel. These are metals which are high energetic metals, which when they oxidize they release a lot of heat, are used in rocket fuels, especially in solid rocket motors. Okay. aluminum, magnesium, even boron is considered as a fuel under in these rocket propellants. Okay. Other unusual fuels here which are not hydrocarbon based are one is hydrazine, which we saw as a monopropellant that is used in small liquid propulsion systems. In fact, hydrazine can be used both as a monopropellant and as a bipropellant. It can decompose on its own, releasing energy when sprayed onto a catalyst. It can also be oxidized with additional oxygen, okay, because it decomposes into nitrogen and ammonia and hydrogen. It can be further oxidized. Okay. There are other interesting fuels also here. You have wood, okay, which if you take wood or what we refer to as biomass in general, including agricultural residues and variety of forest residues, they all have about the same composition, which is approximately CH 1.4 0.6. So a kilogram of wood requires about 6.5 kilograms of air for complete oxidation, and other examples here include various forms of decomposed or decomposed wood, which is peat, which eventually becomes coal, okay, and anthracite. So in this hierarchy of things, you start from organic residue, which is CH 1.4 0.6. As you go down the list, hydrogen and other volatile components are slowly stripped off, and you are left with almost pure carbon when you get to anthracite coal. The oxygen, the air to fuel ratio for that is about 12, okay, which is again C plus O2 goes to CO2, the ratio with air. So it is O2 plus 3.76 nitrogen. So air, what is written here is 4.76 moles of air, which is 1 mole of oxygen plus 3.76 moles of nitrogen. Okay. The simplest another way to look at stoichiometry, because the numbers are very different for different fuels, a normalization that is practiced is called the equivalence ratio, which is defined as the oxidizer to fuel ratio at stoichiometry divided by the oxidizer to fuel ratio, the actual oxidizer to fuel ratio. So phi equals 1 is stoichiometric, phi greater than 1 is fuel rich, and phi less than 1 is fuel lean. This is the most common convention, but you may also find the opposite, okay, but this is the most common convention. But one takeaway is that watch out for the definition when you are drawing conclusions. Okay. So to apply the laws of thermodynamics, we saw that we need measures of enthalpy, we need measures of internal energy and so on. So essentially what we need is a way to keep track or bookkeeping of energy is required, okay, to calculate the equilibrium states. So one question that we need to answer before we can do a calculation is what is the energy change associated with the transformation of reactants to products. Okay. So let us take a simple case, which is methane burning in air. I have been careful in not writing the products as CO2 plus 2H2O. Remember that what we saw in the previous slide is only a statement of stoichiometry. Okay. So what we saw here is only a statement of stoichiometry. When you actually run the reaction, there is no guarantee that you will get the same products. Okay, you will get a variety of products. Okay, so this conversion of reactants to products in the context of combustion involves a large increase in temperature. We know that typically the starting mixture has a temperature of, this is at room temperature 300 kelvins, and increases to about 2200 kelvins with air and to about 3200 kelvins with oxygen. Under such high temperatures, dissociation will be significant. Carbon dioxide will not remain as carbon dioxide at 2200 or for that matter 3200 kelvins. So it will dissociate into carbon monoxide and oxygen. But under adiabatic and constant pressure conditions, well, there is no, so one thing that we need to keep in mind is that when these products can dissociate at high temperatures. So under adiabatic and constant pressure conditions, we know that the enthalpy of the system should be constant by application of the first law of thermodynamics. So the enthalpy of the reactants must be equal to enthalpy of the products, but note that the products are at a much higher temperature than the reactants. Okay. Therefore, the products have a very large sensible enthalpy and the reactants do not. So therefore, the sensible enthalpy of the products is much higher than the reactants, and the question is what is the source of this energy. This is nothing but the net difference between the energy that is required for breaking the bonds between the reactants, okay, and the energy that is released when the bonds are formed between the products. Okay. So the reason why something is a fuel and something is an oxidizer and something is a reactant and something is a product is because the total amount of energy that is required to break the bonds between the reactants will be smaller than the energy that is released because of the formation of the products, and that is why these reactions are exothermic and therefore of relevance to combustion. Okay. So now we have a variety of oxidizers, variety of fuels depending on whether you are looking at liquid propulsion systems or gas turbines or solid propellant rockets. So there are variety of oxidizers and fuels. So a simple way to keep track of the idea of this energy associated with reactions is through the idea of formation enthalpy. Formation enthalpy is nothing but the enthalpy change associated with the formation of a molecule starting from its elements in their naturally occurring form at a constant pressure of 1 atmosphere and a standard temperature of 298.15 kelvins. Okay. So the elements in the naturally occurring form are taken to have a formation enthalpy of 0. Okay. This is just a simple way of bookkeeping, okay, and this will give you a simple demonstration of the idea. We will look at the same reaction. Of course, now I am assuming that the products are these for demonstration, but in realistic cases CO2, H2O will dissociate and you will have a variety of products. Okay. So in this reaction, oxygen and nitrogen are in the naturally occurring elemental form, and hence is a formation enthalpy of 0 according to the definition. And formation reaction for methane, remember that the definition of formation reaction is that the molecule should be formed from its constituent elements in the naturally occurring form. So methane has carbon and hydrogen. The naturally occurring form for carbon is carbon in graphitic form, and for hydrogen is gaseous hydrogen. So the reaction is C plus 2H2 goes to CH4. The enthalpy change associated with this reaction is the formation enthalpy of methane. You can imagine conducting this reaction in a bomb calorimeter and measuring the enthalpy change. In fact, what is actually done is that you, using a bomb calorimeter, you measure the enthalpy of combustion of methane. From that you can back calculate the enthalpy of formation of methane. Okay. This is a simple strategy. For example, if you have an exotic fuel which is a new molecule, the simplest way to get the formation enthalpy is to oxidize it completely using air or oxygen, measure the enthalpy of combustion and back calculate the formation enthalpy. Okay. Similarly, for carbon dioxide you can conduct this reaction and get the formation enthalpy, and so on for other components. Remember that the naturally occurring form for water is liquid water. So the enthalpy change associated with the boiling of water must be accounted for depending on whether you are interested in combustion products in vapor form or in liquid form, usually in the vapor form. Okay. The simple idea is that now the chemical reaction at the top of this page can be expressed as a linear combination of these three reactions. So the reaction R is reaction 2 plus twice reaction 3 minus reaction 1. Therefore, the enthalpy change for the reaction R is the enthalpy change for reaction 2 plus twice the enthalpy change for reaction 3 minus the enthalpy change for the reaction 1, basic ideas from energy conservation and thermodynamics. Okay. So from here we can calculate the enthalpy of combustion or the enthalpy change for this reaction, which is, as I have indicated here, is negative 56.5 kilojoules per gram. It is negative because it is exothermic. The energy required to break the bonds of methane and oxygen or the is smaller than the energy that is released when the bonds of carbon dioxide and water and other product molecules are formed. Okay. Well, this is something that I already mentioned. This is the easiest quantity to measure, the enthalpy of combustion. So what is usually done is you measure the enthalpy of combustion, especially when you have a new molecule for which you do not know the formation enthalpy. So you know the enthalpy of combustion. From there you can back calculate the enthalpy for the fuel molecule.